Hello, I'm Norman Wildberger, and today we're going to talk about three-dimensional affine geometry in the context of transformations of it. The transformations we're going to be talking about are very simple transformations. They are linear transformations given by 3x3 matrices. So it's really the algebra of 3x3 matrices and its interpretation as motions of our affine space that we're going to be studying. I'm going to start out by looking at rather particularly simple kinds of transformations and then working our way up gradually to a more detailed understanding of more complex ones. The basic algebraic ingredient is the multiplication of a 3x3 matrix with a vector. Our vectors are written as column vectors. There's our matrix consisting of 9 entries, which I've labeled A, B, C, D, E, F, G, H, and I. And this is our definition of how that matrix multiplies with that vector to give another vector. First entry is AX plus BY plus CZ. The second entry is DX plus EY plus FZ. And the third entry is GX plus HY plus IZ. So that's a new vector, starting with this vector, ending up with this vector. And we can write that in notation if we say let that matrix be the matrix A, and this vector be the vector V, and this vector, or this one, the vector V prime, then we just write A times V equals V prime. Now this purely algebraic definition has two slightly different interpretations. One of them is a kind of active interpretation, and the other one is a little bit more passive. So the first one is, we can think of this as being a linear transformation in that it sends a particular vector V to another vector. So we can think of it as a motion of our three-dimensional space. In our three-dimensional space, a vector is determined by a triple of numbers, x, y, z. So this actually represents a vector, and this will represent a different vector. And the transformation that sends the vector V to the vector V prime, we think of that as a motion of the vectors in space. So it's actively moving things around. There's another interpretation of what is going on here. And that interpretation is one that we've also seen before. It's the change of coordinates idea. The idea that x, y, and z represent coordinates of a point, and the new coordinates x prime, y prime, z prime reflect the new coordinates of the same point with respect to a different orientation. So in this picture, what we are doing is we're thinking of having an initial frame of reference, say given by vectors e1, e2, e3, and then changing our point of view, changing our orientation to the same ambient space. So instead of describing things with vector x, y, z, we describe everything in a new, perhaps rotated way, new vector x prime, y prime, z prime. So the objects in the space have changed, only our orientation in that space has changed. Both of these are legitimate interpretations of what's going on here. Today we're going to talk more about the active approach, because then we can actually think about moving things around. Maybe it's a little bit easier to visualize when you're starting out. So we're going to adopt the idea that what's happening here is the whole space is being transformed by the action of multiplying by this matrix A. So what we have in mind is something like this. We have fixed axes, x, y, and z, with fixed basis vectors e1, e2, and e3. And here is some random vector in our space. Call it V. And we're thinking of this transformation of multiplying by the matrix as an actual movement of the vectors in this space. So T is a transformation that inputs one vector, that vector V say, and outputs a second vector V prime. Let us say that green one. So it's moving the vectors around. And if we multiply by a matrix, like we're talking about, then the transformation has particularly simple properties. It's what's called a linear transformation, and that means that it satisfies these two basic properties. That T of a sum of two vectors is T of a V plus T of W, and that T of a multiple of a vector v is that same multiple of t of v. Now, to make sense of this, it's important that we are thinking about our transformation as acting on vectors and not on points. And so we're going to do that. We're going to think of our transformation as acting on vectors, just as in this picture here. Let's give an example so we can explicitly see what it actually looks like. Here's a transformation that sends a vector v to what you get when you multiply by this particular matrix. So there's the matrix A, say. There's our vector v, coordinates x, y, and z. And here's what happens when we multiply that matrix by that vector. We get this vector. And this is how it looks like in general. We have combinations of x, y, and z in each of the three entries, linearly appearing. Only x's and y's and z's, no powers of x or y or products. And the coefficients are just rational numbers. Now, this particular transformation is completely contained in the information of what happens to the three basis vectors. So if you look at the E1 basis vector, which is 1, 0, 0, and you plug x equals 1, y equals 0, and z equals 0 into here, you're going to get just this column here. You're going to get 1, minus 3, 2. The first column of the matrix A. If you apply the transformation to the second basis vector with entries 0, 1, 0, then you're going to pick up the second column. And if you apply it to the third basis vector with entries 0, 0, 1, then you get the third column over here, 2, 1, 7. So knowing the transformation is equivalent to knowing just what happens to the three basis vectors. And physically, the parallelepiped family formed by the three basis vectors is moved to another family of parallelepipeds just determined by what happens to those three basis vectors E1, E2, E3. So let's start out by looking at some simple examples and working our way up. The simplest possible linear transformation is perhaps the identity transformation, which simply sends a vector v to itself. And the matrix that accomplishes that transformation is this identity matrix, which has ones down the diagonal and zeros everywhere else. A generalization of the identity matrix is to the diagonal matrices with constant diagonals. So this transformation sends a vector v to lambda times v. Each of the components is multiplied by lambda. And physically what that does is it scales the entire space. It dilates all the vectors by a factor lambda. If lambda is bigger than 1, then we're getting bigger. If lambda is less than 1, we're getting smaller. If lambda is negative, then we're kind of inverting also. Dilations are a closed system. So the whole family of all possible dilations are closed under two natural operations on transformations. One of them is composition, and I remind you that T circle R, T composed with R, is by definition what you get when you act on V to get first of all R of V and then T of R of V. So it's R followed by T. We kind of read this way and we write it this way. The composition of transformations corresponds to the matrix multiplication of the matrices. Another operation that we can define on transformations is the sum. So we can define T plus R, if T and R are linear transformations, to be the new transformation which takes a vector v and sends it to T of v plus R of v. This is a vector, this is a vector, so it makes sense to add those two vectors. And in terms of the matrices, the sum of the transformations just corresponds to the sum of the matrices. So our two basic operations are essentially matrix addition and matrix multiplication. And now when you think about those two operations just acting on this particular kind of transformation, a diagonal transformation with constant diagonal, let's say all twos, or all 3's. If we multiply the matrix with all 2's times the matrix with all 3's, we get the matrix with all 6's down the diagonal. And if we add those two matrices instead, we get the matrix with all 5's down the diagonal. So the dilations, these matrices here, are acting just as numbers do under the operations of addition and multiplication. So inside our rich family of 3 by 3 matrices, we have a very special family of matrices which are particularly simple. They're just the diagonal matrices with constant diagonal. And they form a copy, if you like, of our field of rational numbers. For every rational number, there's such a matrix. And the arithmetical operations of the rational numbers are completely reflected in the matrix operations restricted to those particular diagonal matrices. Now let's consider a slightly richer family of dilations, ones that are also represented by diagonal matrices, but this time with arbitrary entries down the diagonal. We'll call these mixed dilations because these three numbers do not have to be the same. They can be completely arbitrary. And what a matrix like this does on a vector like this is it multiplies the first entry by lambda 1, the second entry by lambda 2, and the third entry by lambda 3. So the three axes are still being maintained, but there's different scaling occurring on each of the three axes. So for example, here's a picture of a particular transformation like that, where the matrix is this one here. There's our original axes, x, y, and z, with scaling as shown. And here I've shown you a little parallelepiped, which is the unit parallelepiped, one in each direction. All the sides are parallel to the axes. And I've shown you what happens to this parallelepiped when you multiply every vector by this matrix here. This matrix scales the x component by a factor of 2, scales the y component by a factor of 3/4, makes it a little bit shorter, and scales the z component by a factor of 3. So the box is elongated by a factor of 2 in that direction, squished a little bit in the y direction by a factor of 3/4, and stretched in the z-axis by a factor of 3. So we go from that box to that box. And maybe I should mention that the volume of this box and the volume of this box are related in a pretty simple way. The volume here is just 2 times 3/4 times 3, which is also the determinant of this particular diagonal matrix. So these mixed dilations are now a richer family. They include the pure dilations that we talked about before, but they're a little bit larger family. And they're also closed under composition and addition. If you multiply any two diagonal matrices, you still get a diagonal matrix. And when you add any two of them, you still get a diagonal matrix. This is a rather rich and important family of matrices. And one of the sort of large-scale programs in linear algebra is to try to relate general matrices, arbitrary ones, to ones in this family. It's going to be a theme that will eventually be occurring here in linear algebra. The idea that a general matrix is in some sense, or sometimes is in some sense, a lot like one of these kinds of matrices. How to make that connection will become an important theme. Now let's have a look at some simple examples of reflections. This matrix here is one of the kind we've been talking about. It has only diagonal entries, but the diagonal entries are 1, 1, and -1. When we multiply this matrix by that vector, we get x, y, minus z. Everything stays the same, except that the z component is replaced by its negative. That means that geometrically what's happened is that a vector v is sent to its reflection in the horizontal xy plane. So the xy component has stayed unchanged, but the z component has gone from 3 to -3, or whatever. So there's v, there's t of v, that's reflection in the xy plane. And if we do it again, then we just get back to where we started. Here's another example of a reflection. In this case, the matrix has entries -1, 1, and -1, and x, y, z is sent to -x, y, -z. This is also a reflection, but of a different kind. The y-coordinate has stayed unchanged, but the x and the z coordinates have been multiplied by -1. What does that mean? Well, here's the x, the y, z axis, the y-axis in this direction. So what's happened here is that if we take a vector v and think about the plane through v that's parallel to the x and z axes. Now what we're doing is reflecting that vector v in that plane around that point. So the y component stays the same, but the x component has changed to its negative, and the z component has also changed to its negative. We are reflecting this point in the line of the y-axis. Another way of saying what's happened is that we take the vector v, drop a perpendicular to the y-axis, and then go an equal amount in the opposite direction. That's another way of saying what the reflection does. So we have reflections in planes, and we also have reflections in lines. And so if this is a line, then the image of this point would be this point. The image of this point would be this point. The image of this point will be this point. We're just reflecting everything in the line. Now let's have a look at some simple examples of another kind of transformation called a projection. And we've already talked about this kind of transformation before when we were talking about how to visualize three-dimensional space. We essentially projected three-dimensional objects onto a plane. That's what we're going to do here. So this example here, where the matrix has ones along the diagonal, except in the third spot where there's a 0. It takes a vector x, y, z and maps it to the vector x, y, 0. So the x and the y components haven't changed, but the z component has gone from whatever it was to 0. It means essentially we're dropping a vector onto the xy plane, directly below it, or perhaps directly above it in this case. Here is another kind of projection, which is not a projection onto a plane, but rather a projection onto a line. Here we have diagonal entry 0, 0, 1, sending a vector x, y, z to simply 0, 0, z. Now what's happened is that the x and the y coordinates are mapped to 0, and the z coordinate has stayed unchanged. Now what happens is that the x and the y coordinates have been mapped to 0, but the z component stays unchanged. Pictorially what happens is, here's x, y, and z, here's our random vector v. We are dropping a perpendicular to the z-axis, and we're mapping v to that vector t of v. So there used to be an x component, there used to be a y component. Afterwards, there's no x, there's no y component. We're purely in the z-axis. But the z coordinate is the same as it was before. In other words, we're still staying on the same horizontal plane that we were starting at. So in three-dimensional space, if that's the z-axis, for example, and here's some vector, then our projection just sends it to that point there, in other words, to that vector there. So every vector is projected onto the z-axis. It's a different kind of projection because the image is a one-dimensional line. Before, in this other example, the image was a two-dimensional plane. But they're both projections, different kinds of projections. Now let's talk a little bit about rotations. I'll just give you an easy example to start off with. Rotations are a little bit different from the other examples because they really require a notion of perpendicularity. They require some metrical information to set up what a rotation is. But still, it's a pretty familiar kind of object, and of course very important for applications. We're going to have a lot more to say about rotations in a subsequent lecture. But let's start off by giving you a simple example of a rotation as a linear transformation. So here is a matrix which has some sines and cosines in it, and it represents a rotation about the z-axis. So there's the z-axis, x and y, and what this is doing is it is rotating the space around the z-axis. If this is the z-axis, a vector like this is being rotated around. So planes which are horizontal, parallel to the xy plane, are fixed but rotated. Let's have a look at the actual form of it. There's a 2x2 rotation matrix in that corner there, and the rest of it has some zeros and ones. And the effect is that the third component is just z. So the z component stays exactly where it is, but the x and the y components get rotated around just as they do in a two-dimensional rotation. So in the xy plane, we're just rotating as usual by theta, in the way we've already talked about in the 2x2 rotation case. This is rotation by an angle theta around the z-axis. But we don't have to choose the z-axis, we can choose other axes too. Here's an example of what a rotation around the y-axis looks like. It's the same kind of form, except that now there's a 1 in the middle there corresponding to the y-coordinate. And if you remove the row and column through that 1, then you still get this 2x2 rotation matrix, cos theta minus sine theta, and cos theta. While rotations around the three coordinate axes are relatively easy to describe in this kind of way, rotations about arbitrary axes are much more challenging to describe. An important task of linear algebra is to try to understand that more general situation. And eventually we're going to do that, but not quite yet. Let's have a look at rotations from a rational point of view. There's a slight difficulty with this picture, right, which is that even if we're just concerned with rational coordinates, introduction of this angle theta and these transcendental functions cosine and sine mean that we have to venture forth out of our number system. We have to move from the rational numbers into the so-called real numbers. And there are a lot of conceptual difficulties with real numbers that are often sloughed under the carpet a little bit. But even practically, in terms of explicit calculations, these kind of numbers that appear when you use these functions are truncations of real values. So you're necessarily losing information when we take this approach to rotations. But as I've mentioned to you before, there's another alternative which is in many cases superior to this point of view. Let's have a look at what it looks like with that other approach. So rational rotations are true rotations purely within the rational number system. And they are given by the Pythagorean formulas for points on the unit circle. So given a rational number h, 1 minus h squared over 1 plus h squared and 2h over 1 plus h squared represent a point on the unit circle. That gives a rational parameterization of the circle, as we talked about earlier. So we can use that to create a rational form for a rotation. And here's what it looks like. This is an exact analog of the thing I did on the previous slide, except instead of angles and cosines and sines, we have these rational functions of a rational parameter h. And it also defines a rotation for us. A rotation of space, which is a rotation around the z-axis, by a half-turn h. Not an angle now, of course, because we're talking about a different framework for measuring rotations. Here's what the half-turn looks like. So if we just look at the xy plane, which is being rotated, the z plane is fixed, then a half turn of 0, h equals 0, corresponds to nothing happening. It's the identity. There will be half, there will be 1, there will be 2, 3, 4, 5, 6, 7, sort of piles up towards infinity as you get close to that point. And on the other side, it would be exactly the negatives of those. Minus a half, minus 1, minus 2, minus 3, minus 4, minus 5, and so on up to minus infinity in that direction. So it's a nonlinear scale, admittedly, but it has a great advantage that it's purely accessible within the rational number system. You don't have to have any understanding of irrational numbers or extension fields to talk about very explicit rotations. And furthermore, they are 100% accurate, these formulas, as opposed to the other one where you're always generally using truncations and approximations. So here's a rotation around the x-axis, for example. It looks very much the same, except now the x-coordinate is being maintained, and it's the y and the z coordinates which are being rotated. Here's a picture for that, x, y, z. the x-coordinate is being maintained, so if we think of the x-coordinates coming out here, that's the same. And in the y-z coordinate, we are rotating by a half-turn h. So this matrix moves the y and the z coordinates around in a rotating fashion, but leaves the x-coordinate fixed. We're going to have quite a lot more to say about rotations when we think about them with this half-turn formulation later on. The projections that we had a look at, very simple projections, they were all perpendicular projections. That is, we were projecting perpendicularly onto a plane. In many situations, we want something more general than that. We have a plane, and we have a direction, which is not necessarily perpendicular to the plane, and we want to project onto the plane. That was exactly the kind of parallel projection that we were talking about when we want to represent a three-dimensional object on a two-dimensional plane. The light rays coming in don't necessarily have to be parallel to the plane that we're projecting onto. So our setup is that we start with the plane with the equation ax plus by plus cz equals 0. There it is right there, the plane pi. And we choose a direction for projection, given by a vector v, coordinates L, M, and N. There's our direction v. There's the line through the origin through v. It's not necessarily perpendicular to the plane pi. Now, given a vector u, we want to calculate what is the projection of u onto the plane pi in the direction of v. So we're allowed to add or subtract multiples of v to get onto the plane. So there's our arbitrary starting vector u, x, y, z. And we're going to try to find a multiple lambda so that u minus lambda v lies on the plane. So we're going to subtract some multiple of v from u to end up on the plane. And u minus lambda v, that's this vector, minus lambda times this vector. We want that to be on the plane, so it should satisfy the conditions of the plane. That means if we take a times x minus lambda L, plus b times y minus lambda m, plus c times z minus lambda n, we should get 0. And that's a condition on lambda that we can solve for. It's a linear equation in lambda, so it's very easy to solve for lambda. We get all the stuff involving lambda on one side, all the other stuff on the other side, and then we just divide. So we get ax plus by plus cz in the numerator, and the coefficient of lambda is al plus bm plus cn. That ends up in the denominator. And provided this denominator is 0, we have solved for lambda. What's the meaning geometrically of this condition that al plus bm plus cn is not equal to 0? That's just the condition that the vector v is not lying in the plane itself. So we don't want a situation where we have a plane like this and the direction vector is actually in the plane. Then it wouldn't make any sense to project in that direction onto the plane. The vector of v has got to be in some different direction, and that guarantees that. Alright, so we have lambda. So u minus lambda v, that's our projected vector, has the form, there's u minus lambda times v. That's the projection p of u as a function of x, y, z. It's a linear function in x, y, z, and it's a vector that we can now write as a matrix times the vector x, y, z. And here's what we get. So please check that this is in fact correct. There's the denominator that we had before, and then the three entries in terms of x, y, and z can be expressed as x, y, and z times this matrix. So for example, the first entry would be this times x plus this times y plus this times z. So this matrix, this combined matrix here, this one divided by the denominator, that's our matrix A. That represents the projection onto the plane ax plus by plus cz equals 0 in the direction or via the direction v given by L, M, and N. So it depends both on the plane A, B, C and on the line or vector with entries L, M, and N. And it's quite a nice expression. So here are a few properties of this projection onto a plane. First of all, the actual direction vector of the projection, the vector v, if we project it, we're going to get the 0 vector. Secondly, if we start off with a vector u which is already on the plane, then when we project it on the plane, well, it doesn't go anywhere. It's already on the plane. So p of u equals u. And in fact, that's precisely when u lies on the plane. So if p of u equals u, then u has to be on the plane. Because if it's off the plane, it's going to be moved. So it's fixed by this transformation precisely when it lies on the plane. And these two imply that p squared of u equals p of u. If you start with any vector u and you project it, and then you project that again, so in other words you're doing p twice to the original, you're still in the same point. Because after the first time you're on the plane, and then when you do it a second time, you're staying where you are. So this is a property of the projection, that the square of the projection is equal to the projection itself. Now there's a second projection associated to our plane and our line. So if there's the origin and there is the line emanating from the plane, then we've just been talking about the projection of space onto the plane via the line. So given a point, we map in the direction of the line and map to the plane. The other possibility is to start with a point and map towards the line. But in what direction? Well, in the direction of the plane. So what that means is we start here and we move in the direction that's parallel to the plane. So you think about translating that plane so it's over here. Then that translated plane will intersect that line in a unique point. And that's where this point is sent to. So you can just think of this plane as being translated. Whoa, like that, right? Okay. That's how we project onto the line. Let's call that projection R. So this is the projection onto the line, which is the multiples of the vector v. We'll use the same notation as before. V is the vector lmn. In the direction of the plane pi, ax plus by plus cz equals 0. And here's the same picture that we had before. There's the plane pi. There's our line L. Here's our starting vector u. Here's the vector p of u that we've just determined in the previous slide. That's the projection onto the plane. Now we want to determine the projection r of u onto the line, also in the direction of the plane. So in other words, this vector here is actually going to be parallel to this vector here. This is a parallelogram. Because that vector p of u lies in the plane. So that's the vector that we're going to use to go from u to the line. And that means that the vector u is the combination of r of u and p of u. It means we don't have to go through some more work. We can use what we've already established about p of u to find out what r of u is, because r of u is just going to be u minus p of u. Now if you look on the previous slide, our formula for p of u, not the final formula, but one of the intermediate formulas, was that it was equal to u minus, there was lambda v. So if we take u minus lambda v, well then we just get lambda v. So that means that this projection onto the line, which we're calling r of u, is given by this expression. And if we write that as a matrix, what do we get? Well, the top entry here, what will the top entry be? The top entry will be L times this. So that's AX times L, that's that entry, plus BY times L, that's that entry, plus CZ times L. So that's that multiplied by L, once we've multiplied this plus this plus this. That's the common denominator. And we get this matrix, which is even simpler than the one that we had before. This is a very attractive matrix, and some features of it. First of all, it's a rank 1 matrix, which means that all its rows are multiples of each other, and all its columns are multiples of each other. And in fact, you can see that the column here, AL, AM, AN, if we take out the common factor A, that's really just the vector LMN times A. While the second column is LMN times B, and the third column is LMN times C. So all the columns are multiples of the vector V. Which is not surprising, because the columns are just the image of the basis vectors under the transformation. And we're mapping onto the line V, so all those images have to be multiples of V. So it's not surprising that we're getting multiples of V there by just pointing it out. And the rows are all multiples of the row vector ABC. There's L times ABC, there's M times ABC, there's N times ABC. And ABC are the coefficients of our plane. It's a rank 1 projection. It's a kind of an important object. So now we've established different kinds of projections. Closely related to the idea of a general projection is the idea of a general reflection. If we have a plane, then the usual reflection is in terms of a perpendicular direction. We drop a perpendicular and then go an equal amount to the other side. But that's only a very special case of a more general type of reflection that is determined by a general direction. So let's say we choose this as our direction, then given any point, we can go in that direction to the plane and then an equal amount to the other side. That's also a reflection, but it's a non-perpendicular kind of reflection. Here's how that looks. So let's call the reflection S. It's going to be across the plane pi, same plane as before, ax plus by plus cz equals 0. There it is again. And the direction that we're going to choose is still the vector VLMN, that direction there. Here's our vector u as before. And here are the vectors that we've already found of projection. The projection onto the plane, which we called P of u, and the projection onto the line, this vector here, R of u. Now what we want to do is we want to reflect u in the plane. So that means we go to the projection and then go an equal amount to the other side. Now this vector here is parallel to this vector. That's the vector R of u that we've already found. So to go from here to there, what we need to do is we need to go backwards along R of u, in other words, subtract R of u, and then we need to subtract R of u again, because we're going an equal amount on the other side of the plane. So in terms of algebraically, we know that u is equal to R of u plus P of u. That's the projection onto the plane. That's the projection onto the line. So what I've just said is that the reflection S of u is obtained by starting with u and subtracting 2 times R of u. Right there. Well, we already have the expression for R of u. There's the vector u that we're starting with, coordinates x, y, z. And R of u is this thing here, and we have to multiply it by 2. So minus 2 over this times that matrix times x, y, z. Now this can also be written as a matrix times something. We can write that as the identity matrix times x, y, z. So what's really happening here is that we're combining the identity matrix with this matrix. So we're really taking the identity matrix minus 2 over this times that matrix and combining them. Well, when you do that, you get a third matrix, and this matrix is the matrix for the reflection S. And here's what it looks like. We still have AL plus BM plus CN in the denominator. And you can check, please check, that the entries of the matrix that you get by taking the difference here look like this. In this corner there's minus AL plus BM plus CN. And then there's a similar thing down the diagonal where the minus sign in here is in the second position and here in the third position. Otherwise this expression looks just like this denominator here. And here, these entries here look just like the entries here, except there's a minus 2 in front of them each. Minus 2BL, minus 2CL, minus 2CM, minus 2BN, minus 2AM, minus 2AN. So that is a general expression for a generalized reflection, not necessarily perpendicular reflection. Reflection in the plane pi in the direction phi. Now, just as we can reflect in the plane pi, we can also reflect in the line L. So the reflection, let's call it T, across the line L, which is the same line as before, the line spanned by the vector V. The V is LMN vector. And the reflection in the direction of the plane pi, AX plus BY plus CZ equals 0. So our picture is that there's our vector u that we're starting with. There's the line L in the direction V. We've already obtained the projection onto the plane. That was P of u. It's right there. And we've obtained the projection onto the line L. That's R of u. That's right, that vector there. Now we want the vector that we get by going an equal amount on the other side, from here to here. That vector there. That's the reflection of this vector in the line L. We'll call it T of u. Now these differences here are exactly P of u. This is exactly the midpoint between these two. And so one way of saying what the relationship here is to say that, well, this vector u and this vector T of u have midpoint vector R of u. So in other words, as an affine combination, R of u is going to be 1/2 of u plus 1/2 of T of u. It's expressing the fact that this is the midpoint of these two. But this is an algebraic relation that we can solve for T of u, which is what we're interested in. We know R of u already. So T of u is going to be 2 times R of u minus u. What's R of u? Well, there's the matrix that does the R operation. The R operation is the projection onto the line. There's 1 over this times that matrix times the vector u. And we need to take 2 times that, so there's a 2. And we still have to subtract u at the end. Okay, it's even simpler than before, I think. Again, there's the identity matrix. We're subtracting this matrix and then subtracting the identity matrix, and we get a new matrix, and it looks like this. There's 1 over AL plus BM plus CN in the denominator, and then the matrix looks not so much different from the previous one. Now there's an AL minus BM minus CN here, and then there's a plus entry in the second component and a plus entry in the third. Otherwise, these are just like the denominator there. And here we have 2BL, 2CL, 2CM, 2AM, 2AN, 2BN. That's the matrix for the reflection across a line in the direction of a general plane. Now it's quite interesting to see what those general formulas look like in the special case when we actually are talking about a perpendicular projection or reflection. The formulas become simpler. So first let's introduce the important notion of perpendicularity. We've said that affine geometry is really the main framework for linear algebra, and that's correct. But in many applications, the usual notion of perpendicularity plays an important role. However, I should just tell you that later on we're going to see that there are other possible notions of perpendicularity. So the one that we're going to introduce now is the main one for most applications in three-dimensional space, but there are also other possibilities too. So what is the definition? Let's frame it in terms of two vectors. If we have one vector ABC and another vector DEF, then we say that these vectors are perpendicular precisely when AD plus BE plus CF equals 0. That's our definition of perpendicularity. Now that might not correspond immediately to you as the same as the obvious sort of geometrical intuitive idea of perpendicularity. And at some point I'm going to have to explain to you why this is a reasonable notion of perpendicularity. But for now, let's just accept it as a definition. This is how we're going to define vectors to be perpendicular. So for example, here's a vector 1, minus 2, 3. Here's another vector 4, minus 1, minus 2. And since 1 times 4 plus minus 2 times minus 1 plus 3 times minus 2 totals to 0, these vectors are perpendicular. And if you take a standard Euclidean framework where you really have three axes which are perpendicular in the usual sense, equally spaced in the usual sense, and you draw these vectors or make a little model, you will see that they actually do appear perpendicular in the usual sense. So this is really the right notion. So this allows us to define the idea of a normal to a plane. When is a vector perpendicular to a plane? What does it mean? So here's a plane pi. Let's say it goes to the origin. Here's a vector v. What do we mean when we say this vector v is perpendicular to the plane? It simply means that it's perpendicular to every vector lying in the plane. So every vector lying in the plane, x, y, z, satisfies an equation like this, if this is the equation for the plane. So if the plane is ax plus by plus cz equals 0, it means that every vector x, y, z in that plane satisfies this equation. But that's exactly saying that the vector x, y, z is perpendicular to a, b, c. So the vector that you get by taking the three coefficients of x, y, and z in a plane like this, that is the normal vector to the plane. It's a consequence of this definition of perpendicularity. So we have a plane like this. We can read off the normal direction very simply. It's just a vector formed by the coefficient of x, coefficient of y, coefficient of z. Alright, so now we're in a position to revisit those general formulas for projection and reflection and see what they look like when the plane and the line are perpendicular. Alright, so here's that setup that we've already looked at several times. There's our plane pi with the equation ax plus by plus cz equals 0. And now we're assuming that our direction v, which we were calling L, M, and N before, is actually a normal vector to that plane. In other words, that it's the vector A, B, C. That's the normal vector to that plane. So this is a special case of what we were doing before. So the picture now is that this line is really emanating perpendicularly from the plane. And now these various projections and reflections are all perpendicular. That means perpendicular to the plane. That's perpendicular to this line. So there's a vector u, there was our projection p of u, there was the projection onto the line called r of u, that vector there. Then the reflection in the plane is s of u, and the reflection in the line was t of u. Alright, so we can take the formulas that we have already have, and then we just replace the L with an A, the M with a B, the N with the C, and things simplify a little bit, because then now there's only A, B's, and C's instead of A, B, C's, and L, M's, and N's. So the matrix for the projection onto the plane, P, has this form. 1 over Q times B squared plus C squared, A squared plus C squared, A squared plus B squared down the diagonal. And then the off-diagonal terms, minus AB, minus AC, minus BC, and the other ones are symmetrical. So this is a symmetric matrix. Now, I haven't written it down here, I see, but what is Q? Q was that AL plus BM plus CN term, but now A equals L and B equals M and C equals N. So Q is just the sum of the squares of the entries of the vector. So Q is equal to A squared plus B squared plus C squared. What I call the quadrants of the vector. That's why it's called Q. Okay, and what about the projection onto the line, R of u? Well, there's the matrix for R, also 1 over Q. And now there's A squared, B squared, C squared down the diagonal, AB, AC, BC, AB, AC, BC, also a symmetric matrix. And the reflection in the plane, there's the matrix for it, 1 over Q times this thing. Looks a lot like this, except there's a minus A squared plus B squared plus C squared, A squared minus B squared plus C squared, A squared plus B squared minus C squared. And now minus 2AB minus 2AC minus 2BC, and symmetric on the other side. In many books on linear algebra, these formulas aren't really derived. Special cases of them are worked out. So you take a particular plane and a particular line and you work something out, and you get a particular matrix with lots of numbers in it. Unfortunately, as I hope you're starting to appreciate, the numbers, while they may be simpler to work with, are often less conceptual and less informative ultimately. A matrix like this has a pleasant aspect to it. It's telling you something. There's a pattern to it. The entries are not just random. They have pleasant relationships with each other, and in some sense it's easier to remember what's going on when things are framed in terms of abstract letters or algebra instead of particular numbers. So I encourage you to not be afraid of formulas like this, to really appreciate them, stare at them, and sort of give them some thought. They're often very beautiful and they have lovely properties. For example, we know that the projection vectors have the property that when you square them, you get them, the matrices back again. So p squared equals p, r squared equals r. What about this matrix? What happens when you square that matrix? Well, this matrix represents reflection in the plane, and if you do reflection twice, you end up back to where you started. So if you take S and you square it, you get the identity matrix. And what about the other reflection, T of U, the reflection in the line? Well, T was just equal to minus S. So we've got S there, T is just minus S. Also pleasant, of course, but I haven't written it down separately. Alright, good. So now a few exercises. Alright, just 2 exercises today. The first one is to find some projection matrices for projections onto this plane via 2 different directions. One, a kind of a random direction with respect to the plane, and one, another normal direction to the plane. And also find the reflection matrices for reflection in the plane in these 2 directions. And our second exercise, to find the same kind of projection matrices, but now onto the lines. So we have 2 different lines, the line through this vector and the line through this vector. And I want you to project and reflect in those lines via the directions of the planes, that one there, same one as up here, and the second plane, x plus y plus z equals 0. Just to give you some practice, keep calculating projection and reflection matrices. And you don't need to use the formulas or just copy the formulas. I'm quite happy for you to derive those formulas again yourself. That way you really learn. Next time we are going to expand our understanding here of these 3-dimensional transformations by freeing ourselves from dependence on a particular frame of reference. So the examples that I gave you with dilations especially, where we are emphasizing dilations in the 3 different directions, we want to be more general and consider dilations in arbitrary 3 directions. That's a very interesting situation that's going to open up a whole new domain of things. And we're going to touch base with the second most important problem in linear algebra, okay, which is really the problem of finding the eigenvectors of a matrix. So we're still going to be working in the 3x3 case here, and admittedly somewhat specialized, but it's a very good place for you to develop your basic intuition about that. So we're going to talk about generalized dilations and eigenvectors next time. I hope you'll join me for that. I'm Wildberger. Thanks for listening.